Okay, morning everyone. Sorry for being a little bit late. So I need to start share with the iPad because I want to write something. So first of all, our homework 3 is gonna due on this Friday. So please, if you haven't started, I mean, I would say many students have already started. I'm saying talk to them in office hours, but if you haven't started, this is really like very tight timeline, and you can't like finish it in 2 hours. Probably you're gonna write a beautiful piece of code doing the algorithm logic beautifully, but it's not guaranteed to be correct because you have to test, you have to verify it on the practical data we have provided you. And you do need some like time to run your algorithms on those data set repeatedly to generate the results and write out the report. So timeline is very tight if you haven't started yet, right? Again, please fully leverage our office hours, and we're here to help you. And we have an office hour every weekday. But according to the feedback of our TAs, most of the time the office hour is still empty. So please leverage them. And if you just if everybody just come to office hour on Friday, that'll be very crowded. But we do have like office hours from Monday to Friday, which can effectively kind of like distribute the request and democrat um, uh, prioritize the helping time allows, right? Okay, another thing is about the final project report. Yeah, we'll soon release the due for the final project report. It'll be roughly after or at the end of the examining week. So basically, we'll have a online exam. It's pretty simple and pretty straightforward. And then we request you to submit the final project report summarizing what you have done throughout this semester for your project, right? And for the final project, there won't be any uh, there hardly be any possible for the extension because we have the hard timeline to submit your final grade to the registrar office. They won't allow us to for the delayed submission of your grade. That makes us very hard to grant you any extension for the final project, right? So if you on halfway of your project, you want to do something, please start doing right now. And we definitely don't want to occupy any of your time to prepare final exams. We hope that like you have all the results ready. You just need to spend a morning or half a day to summarize what you have done and submit the report. And that's it. Okay, any question regarding our schedule? Homework assignments and project and anything else? Okay, great. So yeah, we just need to want to be like clear and be prepared for because we're going toward the end of semester, right? So we just want to make sure everything is on track, right? Okay. So let us continue with SVM, right? So in the last lecture, we talked about the dual form of SVM, right? And the motivation. The motivation is that we want to extend SVM to be a nonlinear classifier. So if we do linear classifier, right, it is enough to train a primal form. So what's the primal form? If everyone could like recall with me, right? So the primal form turns out to be just minimize a regularized loss, right? And remember, this loss is kind of very special. It's called hinge loss, right? So you got a trade-off constant C, and you go through every training example. Your hinge loss is something like this, right? Y minus yi, yn, w transpose xn plus b, right? Right. So this directly starts from the primal formulation of the SVM, right? If you could remember, it starts from the soft SVM version, and then you remove the slack variables, and it turns out to become this succinct form, right? And then we'll talk about strategies of optimizing this with respect to WB, which we call stochastic gradient descent, right? But doing this can only allow us to perform a linear classifier because our prediction is here, right? Prediction is based upon the dot product between W and feature vector plus the bias parameter, right? This is the very standard linear classifier. And then we mentioned that, okay, we would like to extend the capability of SVM, right? Want to handle highly nonlinear cases, right? And then the primal training won't be sufficient, right? That's why we resort to another representation of SVM learning, which we call dual form of SVM. Right? Okay, so let us just quickly review what is dual form, right? So we start with this general definition of the primal form, which is a constraint optimization problem, right? Suppose we want to minimize an objective function and subject to a set of M constraints where each constraint is represented by an inequality, right? Like this GI X is called constraint function. We specify that this constraint form to be like GRX less than or equal to 0, right? This is called primal form. And we introduce an augmented function, which is called Lagrange function, which is the objective function f of x plus a linear combination of those constraint functions. And the coefficient for each constraint function, lambda I, is called a Lagrange multiplier. I believe everyone is familiar with this form, right? Everybody has used this before. It's called Lagrange function. And we can show that this primal problem, the constraint optimization problem, it is equivalent to solving a minimax optimization problem on the Lagrange form. Just be careful. 3 things, right? First, in this equivalent formulation, the objective becomes a Lagrange function, which is the original objective plus a linear combination of the constraint functions, right? And then this optimization is not like single, like max min, right? It's actually a nested optimization problem. It's called a minimax optimization. So in the inner level, we maximize the Lagrange function subject to a non-negative constraints over the Lagrange multipliers. And in the outer level, we minimize the Lagrange function with respect to x. Remember, x is the variables we want to optimize in the primal problem. So we're not gonna review like why this is equivalent. The proof is pretty straightforward, right? We just want to recall the fact here, right? So this general constraint optimization problem is equivalent to solving this minimax optimization on the Lagrange function. Right? In the inner level, we maximize with respect to non-negative constraints on Lagrange multipliers, lambda 1 through lambda m. Right? In the outer level, we minimize the Lagrange function with respect to x, but now x doesn't have any constraints. So any question regarding this? Okay, so and for succinct, right? We call this minimax as the primal problem. And it has a dual form. The dual form is just to switch the order of min and max. So basically, I'm gonna minimize the Lagrange function in the inner level, and then maximize the Lagrange function outside. But we still take non-negative constraints over lambda. And we still use the Lagrange function, as the objective. That's it. That is called dual form. And don't ask me why this is called dual. This is like named by mathematicians, right? We just need to memorize the concept, right? We got this primal form. We just switch the order of max mean. We got a dual form, and also we mentioned that actually like switching the order can cause the change of the optimal. In other words, like if you solve the primal, you look at the Lagrange function value at the primal of the dual, it will be lower. It will be upper bounded by the Lagrange function at the optimal of the primal problem, right? And again, we're gonna meet the proof here. The proof is pretty straightforward, but you need to, connect a few inequalities and put them together, and leave the whole proof in the slides and for your reference, right? And here, the spectral property about SVM is that in SVM, the dual problem is equivalent to primal problem. In other words, solving the dual form for SVM is equivalent to solving the primal form. Right? There's no need to specify, okay, the dual solution will end up with a smaller Lagrange function value than the primal solution. Right? That's very nice property. That means that, okay, we can use dual form. We can look into the dual form of SVM and simplify and say what we can get. Right? That's a very nice property, right? So now we can go back to the primal form of SVM. Right? The primal form of SVM is this soft SVM. If we could recall, right? So we have this objective. The objective is half square norm of W, which encourages large maximum margin, right? And this guy is a summation of the slack variables, right? Remember the slack variables, the usage. The slack variables are introduced to allow some examples to break into the margin. Because in a data set where it's not like truly linearly separable, right? And to train a linear classifier for it, right, we have to allow some examples to break into the margin. And for the remaining examples, which are linearly separable, we want to find out a classifier which has the largest margin, right? That's the key idea of the soft SVM. Right? And this COSI, this additional slack variables COSI, allows such kind of flexibility, right? And as to which data points can break into the margin, which data points should outside the margin, right? Be outside the margin. It is determined how the optimal values of COSIs. Right? If you look at the constraint, right, for every training example, we require this function margin to be no less than 1 minus COSI, and COSI must be non-negative, right? If the optimal value of COSI, say COSI star, turns out to be 0, right? And that means the function margin is no less than 1, indicating that the example xi stay outside margin, right? Otherwise, if COSI bigger than 0, that means that xi can intrude margin. Everyone's comfortable, right? I'm just repeating what we have discussed previously. Any question? Okay, great. And this, in an objective function, we want to minimize the summation of those COSIs because we don't want to exclude many examples, right? We don't want to allow many examples to break into the margin. Why? Because it could increase the training error. Okay, so this is a soft SVM objective function, right? So, but just convert it into an equivalent minimax optimization, we can do this, right? And for every training example I, we have 2 constraints, right? And for each constraint, we're going to introduce a Lagrange multiplier alpha I and beta I. And then the Lagrange function would be the objective function, right? This is our original objective function, plus a linear combination of the constraint functions, right? And why do we have minus sign here? Why? Any thought? Why do we have minus sign here? Any guess? Oh, that's fine. That's fine. All right. So we need to associate with like general form of the constraint optimization problem, right? So the general form of constraint optimization is that, okay, I'm gonna minimize some objective function subject to a group of constraints, right? The constraint is defined as GIX less than or equal to 0, right? That's the general definition, right? If you want to apply this guy, if you want to apply this formulation to get this equivalent minimax, right? You have to make sure that your constraint is like some constraint function less than or equal to 0, right? Right? If you take a look at the SVM formulation, you see that actually you have to multiply -1 to invert the direction of the inequality. Right? Does it make sense? Right? You have to move this guy to the left-hand side and then minus sign such that you got some like corresponding GIX less than or equal to 0, right? That's why you have a minus sign in front of it. Any question? Okay. So, and then you just apply the formula, right? We have just discussed, and you require that all Lagrange multipliers to be non-negative. And outside, you're gonna maximize our model. You're gonna minimize the objective with respect to our model parameters, including WB and KCIs, right? And this is our primal form, and then you just switch max min, you got dual form, and then we talk about the series like simplification steps, right? The first simplification is that, okay, I want to look at what if I just solve the inner minimization problem, right? Suppose in the outer level, I have a set of alpha i's, beta i's fixed, right? I want to say like, given this alpha i's, beta i's, what's the minimum of the Lagrange function, right? To achieve the minimum, we can simply set the gradient to 0 and say what we can get, right? If you set the gradient to 0, you will get these 3 facts. Right? You take the partial derivative of L with respect to W, B, and each select variable Ci, you got these 3 equalities. If you just substitute those equalities back into L, you get the optimal value of L, which turns out to be a very simplified form. Right? This simplified form actually is a quadratic form regarding alpha i's, right? You can see that you have the double summation, and each I and this I and j go over every training example, and the summand is the product between the labels yi, yj, and the alpha I, alpha j's. I remember alpha I, alpha j's are Lagrange multipliers, and plus the summation of alpha I. Right? This is kind of like just substitute these formulas and into L. You can immediately get that. Nothing special, right? Just practice, right? And then you get this. And meanwhile, we should respect this succinct form as obtained when you have all this gradient to be 0, right? And I mean that that is why we should put those gradient to be 0 as explicit constraints outside. Right? And then we get our simplified dual form of SVM. Right? And further, we can simplify in that, because in this objective, right? In this objective, we actually don't see beta i's. You have like alpha I plus beta I must equal to C, and beta I must be equal to 0. That equivalent to C, alpha I must be between 0 and C. Right? Once you have alpha I between 0 and C, and beta I equals to C minus alpha I, which will always be non-negative. And you can get rid of beta I. And eventually, we convert the dual form of our SVM to be like this. It's a quadratic convex optimization problem. Right? So see that we're going to minimize this quadratic function with respect to Lagrange multipliers alpha I and alpha j's, right? And subtracted by the summation of alpha i's. And of course, we need some additional constraints. That is, each alpha I must be between 0 and C, which comes from here, right? And the alpha I, yi, their summation must be 0, right? This comes from here, and this guy comes from the, when we solve the inner minimization problem, you take the gradient with respect to the bus parameter to be 0, you have this alpha I, yi summation is 0. So solving SVM is equivalent to solving its dual form in terms of the Lagrange multipliers alpha i's. Any questions so far? Everyone's comfortable? Right. I look at everyone's face is serious. If you don't feel comfortable, just let me know, okay? Or if you want us to clarify anything, just let us know. Otherwise, I feel like, okay, you feel this is kind of straightforward, or you feel like it makes sense and you do need some like deriving some details, that's totally fine. Because this is just a combination of pieces of like simple facts and connect them together, piece them together to get a chain to get this amazing results. Right? So again, I highly recommend everyone to follow the slides and derive everything by yourself, and that will definitely deepen your understanding. Okay, so now let's do not worry about how to solve this problem. This is a classical problem. It's called quadratic convex optimization problem. So you can use any convex optimization package to do this. So let's assume, okay, we have this. Right? And in our homework 4, you will be required to implement an SVM in this, right? But we will give you like some optimization package, like SciPy optimize. You can directly use it. You don't need to write any code to optimize this. Right? So what's the benefit of using this dual form? As we will see, it will enable kernel trick and the nonlinear classification in infinite dimensional space. Right? So you see that how this one can help us so easily to extend linear classifier to nonlinear classifiers. Okay, but before we talk about that, right, let us first consider a more practical problem. If you look at the dual formulation, right, we're actually just solving the optimal Lagrange multipliers. Those alpha i's. So remember, alpha i's are multiplier for constraint functions, right? So they're not directly corresponding to the model parameters W and B. A natural question would be, okay, if I have solved this dual form, I got the optimal Lagrange multipliers alpha 1 star to alpha big N star. How do we recover the optimal model parameters W and B? Right. After all, only when you have WB, you can apply this model and to make prediction, right? Otherwise, you have this alpha 1 star to alpha n star, they're useless, right? You cannot directly use them to make predictions. Okay, how to solve this? And how do we recover WB? Any idea? Right. To recover it, we can first look into the derivation procedure, right? How do we arrive at the dual form? Right? So if we arrive at dual form, we see that okay, in the primal form, right? Sorry, in a complete dual form, we have this max min and a Lagrange function, right? So we talk about want to simplify this dual form, meaning that given the outside, those alpha I, beta I are fixed, we want to solve this minimization problem. To solve that, we take the gradient of the Lagrange function with respect to 0, and we have one fact, right? That is the Lagrange function's gradient with respect to W to be 0. We obtain the first fact that W is a combination of YXI in terms of alpha i's, right? Yeah, if we go back to the previous slide, right? Look at these slides, right? This is our dual form, right? We want to simplify this dual form. That means we want to solving the inner minimization problem first, right? Solving it, meaning that I'm going to take the gradient and set gradient to be 0. And if you take the gradient for W, right, you got W actually equals to this guy, right? Equals to summation of alpha I, yi, xi. And now you got optimal alpha i's, right? You got optimal alpha i's. You just substitute it for alpha I, you get the optimal W. Right? So this one is pretty easy, right? So we just leverage the result from our inner minimization, right? We have already identified the relationship between W and the Lagrange multipliers alpha 1 through alpha n, right? And then you set W, you just substitute for those alpha i's, you got optimal W star. And one interesting observation is that you see that optimal W actually is still a combination of the training inputs, right? It's just a linear combination of the training inputs. This is a very, very important structure, as we'll discuss later. Okay. Then let us look at how do we recover bias parameter B. This one is a little bit tricky, because even if you look at the inner optimization results, right, you won't find any clue to recover B in terms of those alpha 1 star to alpha n star. Why? We can go back again, right? If you take a look at our inner minimization results, oops, right? You see that when you take the gradient of the Lagrange function with respect to B to be 0, because this guy are just the linear function to B. If you take the derivative, B is gone, right? So it's just the fact. It's just the fact that the coefficient of B, which is summation of alpha I, yi, is to be 0. That's it. And those results won't give you any clue about how to recover the optimum B value. Then how do we address this problem, right? How do we use the optimal alpha 1 to alpha n, right, to recover B? Right? So here we have to leverage some fundamental concept in optimization, right, which is called KKT conditions. How many of you have heard of KKT conditions? No one? Okay. Oh, great. Yeah. Okay. Yeah. KKT condition is kind of like a very fundamental, very cornerstone in optimization theory, right? So, but it's not like a very complicated concept, right? It's just to provide you a test suite telling you or informing you if you have arrived the optimal for some problem. Right? So, what is KKT conditions? You basically view them as a set of testing conditions, right? And when we want to solve some optimization problem, right? And because it's always hard to tell whether you have arrived the optimal, right? Especially you're solving a constraint optimization problem. If you're solving unconstrained, that might be easier. You just take a look at the gradient if the gradient is 0, right? But for solving unconstrained optimization problem, things becomes much more complicated, right? We probably need one set of reliable tests and which can tell us, okay, we indeed are at the optimum of this problem, and then we can return it. Or we could not. We should continue searching. So here is the definition of KKT conditions. And there are many, many versions of KKT conditions. And here we just talk about the inequality. Right? And for convex problem. Suppose I have a convex problem, right? Meaning that my objective function is convex and my constraint space is convex, right? So this is the objective f0x, right? And the constraint, I got m constraint functions, f1x, f2x to f big mx, right? And those constraints just follow the general form, like each constraint function should be less than or equal to 0. And then the associated set of testing conditions, which we call KKT conditions, are as follows. So actually we have 4 groups of conditions. First, we want to test if every constraint function less than or equal to 0. It's basically testing whether your particular x satisfy every constraint, right? Second one, we require the lambda. So basically, KKT conditions apply to a pair, x and lambda. X is the optimum, is a variable we want to optimize. Lambda, you can roughly view it as some kind of Lagrange multipliers associated with this x, right? The second condition is testing whether every element of lambda is non-negative. The third set of testing, the third set of conditions are even more interesting, right? Which is called a complementary slackness. So what does it mean? We want to test if the product between every multiplier lambda m and the corresponding constraint function f m of x is 0. In other words, like if any term, like if lambda is non-zero, then f m of x must be 0, right? Or if f mx constraint function is non-zero, then the multiplier lambda m must be 0. This is called constraint, is called complementary slackness. And the last one is actually the gradient of the Lagrange function is 0. So the KKT conditions consist of these 4 groups of conditions. And if for a pair of x and lambda, you test them with this set of KKT conditions, then we can drive some kind of conclusion. Before we see what kind of conclusions we can draw, right? Any question regarding the definition? Any question regarding the definition of this set of these 4 groups of the testing conditions? Everyone's comfortable? Okay, perfect. Okay, so first we call it sufficient condition. So basically, if you can find some x and lambda, right? X and lambda pair for the problem, for this particular problem, right? For this convex constraint optimization problem, right? And if you can show that this pair x star and lambda star hold for the KKT conditions here, we can conclude that X star is a solution to that optimization problem. So it's a very good result. Like if you can find a pair of X and star and lambda star, if they satisfy the KKT conditions, you can claim that okay, X star is one optimal solution for your optimization problem. This is called sufficient condition. But in general, it is not necessary condition, meaning that you probably will have some kind of like solution which doesn't satisfy KKT conditions. You see the difference, right? If your KKT condition is satisfied, then you can draw the conclusion, okay, you find a solution, but not vice versa. You couldn't say like for any solution, optimal solution, they will satisfy the KKT conditions. But there are some exceptions. If you have a nice constraint form, meaning that you can write out your list of constraints as this hyphen form or linear form, then KKT conditions become sufficient necessary as well. So basically, if you have you have enough simpler optimization form, like you have minimize this guy, and your each of a constraint function is just a linear function of your optimization variable X, then the KKT conditions are not only sufficient, but also necessary. Any X and lambda pair you find which satisfy the KKT conditions will be the solution for this problem. And for any solution of this problem, right? And there must exist some lambda such that X and lambda satisfy the KKT conditions. Any question here? Yeah, we're just telling the facts, right? We're not showing why this is proved and how it is proved, right? We want to leverage these facts to help us recover the bias parameter B from the dual solution of SVM. Any questions so far? Okay, great. So now we can use KKT conditions to analyze our SVM solution. Why? In other words, we can view KKT conditions are both sufficient and necessary conditions for SVM case. Why? Any thought? Why? As we just discussed, right? When KKT conditions become necessary, if we have this linear constraints, right? Linear constraints for X. If we take a look at the constraint function for SVM, there are linear constraints to our optimization variables, right? If we can write it down, right? For every, for example I, we want this function margin no less than 1 minus KCI, right? And the KCI must be non-negative, right? And remember, our optimization variables include what? WB and KCIs, right? So you see that this constraint, this inequality is linear in WB and KCI, right? You can easily convert it in this form. Right? We can do it together, right? So if you take a look at here, you will have this guy, right? You have 1 minus KCI minus W transpose yi xi subtracted by yi b less than or equal to 0, right? You have this, right? So you see that our optimization variables includes Ci, W, and B, right? They're just a linear combination. The constraint function is just a linear combination of those Ci's, W, and B. So it follows this form, right? In other words, like you can convert, you can align all those constraints all together, put them all together, you can write down a big matrix version of linear inequality. And I will leave it as an exercise for you guys, right? And you see that it just satisfies this form. Meaning that for SVM problem, right? KKT conditions are both sufficient and necessary to claim you arrive at the optimum. Any question so far? Everyone's comfortable? If you feel a little bit not catch up or uncomfortable, that's fine. Again, we want to explain the detail for you, but to make you totally comfortable and have you like deeply informed, again, we recommend everyone to write down those things by yourself, just like me, just just like what I am doing here, right? And derive everything. It will be crystal clear. Okay, so now that we know SVM, for SVM, the KKT conditions can be used as unnecessary conditions, right? So the basic means like, okay, if we find the optimal of the Lagrange multipliers and model parameters, they must satisfy the KKT conditions, right? Remember, KKT conditions can be both sufficient and necessary, right? Necessary means that, okay, if you got your solution, then the solution must satisfy the KKT conditions, right? Now here, we solve the optimum, we solve the dual form, right? We know that the optimal value of the dual form must satisfy the KKT conditions. And here, we're gonna look at the complementary slackness for the KKT condition. So the complementary slackness basically says that your Lagrange multiplier multiplying with your constraint function should be 0. Let's see if we have this for our SVM solution, what interesting things can we observe? So here, we know that for this guy, right? For this constraints, we have Lagrange multipliers beta I, right? And for this constraint, we have a Lagrange multiplier for alpha I. So when we found the optimal value for alpha I and beta i's, and also the optimal value for W and B, then alpha I multiplying with the constraint function must be 0. Beta I multiplying with Ci must be 0. This is called complementary slackness, right? So if you write down here, it'll be here, right? Beta I star, which represents the optimal value of the beta I, right? And Ci star, optimal value of the Ci, their product must be 0. Similarly, alpha I star, Lagrange multiply for this constraint, right? Regarding the function margin, right? Multiplying with this guy must be 0, right? So we're gonna leverage this fact and combined with the inner maximization problem we derived previously to recover B, optimal B, right? Okay, so through our inner minimization step, right? When we solve L with respect to W, B, and Cauchy, when we take the L gradient with respect to Cauchy and set to be 0, we have this fact that is alpha I plus beta I must be C. By the way, what's C? What does C mean? C is a hyperparameter, right? It's a trade-off between maximizing the margin and also the hinge loss, right? Okay. So now let us put this results together, right? We have the complementary slackness, which are satisfied for the solution of SVM. And we also know that our solution must satisfy the inequality that alpha I star plus beta I star equals to C. This comes from our solving procedure for the inner maximization problem. Right? And let's see, when we combine them together, what can we get? By the way, before we do some kind of inference, any questions so far? Okay, so those are the results, right? So let us find, remember every training example has an alpha G star, right? And alpha G star must be between 0 and C. So let us try to find out some example such that the optimal alpha G is exactly between 0 and C. It's not equal to 0. It's not equal to C. It's just right between them. Let's see such alpha G star. What such alpha G star can bring us. So first, if we take a look at here, right? Because alpha G star is strictly less than C, right? Then it basically means the corresponding beta G star must be bigger than 0, because our beta G is C minus alpha G star, right? Alpha G star is, if alpha G star is strictly less C, then beta G star must be strictly bigger than 0. Then if you look at the complementary slackness, the product between beta G star and C G star must be 0, but beta G star is bigger than 0, then the slack variable is the optimal value, must be 0. Right? It comes from the first complementary slackness that beta G star times C G star must be 0, right? And this guy is bigger than 0. And this guy must be 0. Right? And next, because alpha G star must be bigger than 0, right? Alpha G star is strictly bigger than 0. And according to the complementary slackness here, and this guy must be 0. Here. This function margin for yxg subtracted by 1 plus the CG star must be 0. Okay. And from our previous result, CG star is already 0. That basically means the function margin minus 1 equals to 0. Okay. And W star has already been known. Right? We have recovered WG star at the very first beginning. Then we can solve the B star by subtracting YG from the optimal W dot product with XG. This is how we get the optimal B. We just need to find any alpha G star, which is strictly between 0 and C. And then through the complementary slackness and the constraints, right, we can immediately obtain the optimal B, which is YG subtracted by the dot product between W star and SG. Any question? Okay. And someone might ask, okay, what if I have multiple alpha J's which are strictly between 0 and C? Okay. It's very simple. You can do it. You can do the estimate for B star multiple times and take an average for being stable or robust. Any question? Okay. Yeah, we hope this piece of like a chains of reasoning not too complicated to everyone, but again, the reasoning is simple, but it should leverage multiple facts, right? And you should smartly infer the optimal B based upon those facts, right? Again, please practice with those slides and derive this by yourself, and I'm sure like you get much better understanding about this, right? Okay, so now we have finished the discussion about how to recover the optimal model parameters W and B from the dual solution. Right? Remember, the dual SVM dual only give you the optimal value of alphas, right? Alpha 1, alpha 2, alpha 3, and so on. Right? So now, if you look at the optimal W star, right? We know that it is essentially the linear combination of all the training examples where the coefficient for each training example is the optimal Lagrange multiplier alpha I star. The natural question will be, what if some alpha I star to be 0? That will mean that the corresponding xj, yj will not affect the weight vector at all, right? Because W star is just the linear combination of all the training examples. If the coefficient for one training example is 0, that means this training example doesn't affect the weight vector, optimal weight vector at all, right? Okay. So the weight vector is only determined by training examples with non-zero alpha j star. We call those examples with non-zero alpha j star as support vectors. That's where this term comes from. Support vectors just means, okay, those subset of training examples which really determine the model weight vector. Any questions so far? Okay, and then next, we want to look at where do these support vectors stand? Are they stand like inside the margin, outside the margin, or right on the margin? Right? That's something I will feel interested in. Again, let us leverage the basic facts about the complementary slackness and the constraints we derived and say to infer what are the positions of the support vectors. So we know that for support vectors, their corresponding alpha g's must be strictly bigger than 0, right? And then from the complementary slackness, right? Remember, this is the first complementary slackness. The alpha j star multiplied with the constraint guarding the function margin must be 0, right? Because alpha j star must be bigger than 0, strictly bigger than 0, that means this constraint function must be 0. Okay. In other words, the function margin, yi times this score, right, is equal to 1 minus cosine j star. And cosine j star, the slack variables, is non-negative. Then it means that this function margin is less than or equal to 1. What does this imply? What does this mean? What does it mean like the function margin for a example xi is less than or equal to 1? Yes, exactly, right? Remember our SVM formulation, right? When the function margin is no less than 1, it means that this example is outside margin or on the margin, right? But if it is less than 1, it means it breaks into the margin. Of course, if it is equal to 1, it means like it's right on the margin, right? So if we want to have some example to be a support vector, basically means the Lagrange multipliers alpha j for that example must be bigger than 0. The consequence is that this example must stay either on the margin or inside the margin. That's where the support vectors stay. Here we're gonna look at some concrete example. So this is one example, right? So those are positive examples, negative examples. And this one is this black line indicates our hyperplane, right? So we see that there are a few examples. This guy, this guy, this guy, this guy, this guy. They are on the margin or break into the margin. And those examples are actually the support vectors, which finally determine where our linear classifiers stay. Right? On the contrary, the majority of examples stay right away from the margin and from the linear classifier, from the classification hyperplane. They actually have no influence on the classifier at all. So that's an interesting conclusion, right? Actually, the examples who decide where we should place our hyperplane is determined by those outliers. Those outliers can break into the margin or on the margin, right? And for the majority of examples which are well classified by our hyperplane, actually has no influence on the classifier at all. Any question? Okay. So in practice, as you will see, you will verify by yourself in our homework 4, right? You will see the solution tends to be sparse, meaning that most of I star equal to 0. The final weight factor of our classifier is only determined by a few outliers. And those outliers either stay on the margin or break into the margin. That brings some benefit, like, because if we want to represent W star in terms of training examples, we actually do not need to explicitly store all the training examples. You just need to store a few support vectors. Okay, any questions so far? You don't know that. So basically, this is like chicken eggs problem, right? So they are evolving. You are adjusting which examples are stay on the current margin or inside the current margin, which decide the current weight vector, right? And this weight vector adjust. Then the examples or the set of support vectors are changing as well. So you can imagine there's some kind of co-updating procedure inside optimization, and eventually you get your optimal classifier and their position. And they are literally determined by those examples who currently inside or stay inside or break into the margin. Okay, any other question? Yeah, of course. It is possible. It's not like unreasonable. Because as we mentioned, right, support vectors must either on the margin or stay outside, stay breaking to the margin. Right? You cannot predict whether you're gonna correctly still gonna correct the predict that examples. So that means we have non-zero training error. The reason of this actually, although it's kind of a surprising, the conclusions seem surprising, but actually it's not. It's reasonable in that because we want our support vectors, or want our support vector machines to find a classifier which can classify most of the examples. In other words, we want most of the examples to stay outside the margin. We want to maximize that margin. We just allow a set of outliers to break into the margin, from which we can have like training errors, right? And remember, the support vector machines are essentially trying to minimize the generalization error bound, right? The bound consists of the training error plus a term determined by the margin, the VC dimension, right? So actually those examples, those outliers of support vectors which break into the margin, not only determine the position of the classifier, but also determine the training error. It's part of the generalization error bound, right? But also this position also give you a margin, right? Give you a margin which indicates the complexity and indicates the term regarding the VC dimension. Okay? Those all together give you what is the best trade-off between the training error and the VC dimension term, which give you the tighter or tightest generalization error. Any other question? Okay. So now I have finished the discussion about dual form and support vectors. Next, we're going to take a look how those dual forms can be leveraged to extend our linear classifier to be a highly nonlinear classifier. This type of approach is called kernel and kernel trick. So we're going to start with the prediction procedure with SVM dual solution. Right? We know that for linear classifier, if we want to make a prediction, we just need to calculate the score, right? The dot product between W and X and plus bias parameter, right? And from the SVM dual solution, we know that the optimal weight vector W is essentially a linear combination of the training examples, or more explicitly, it should be linear combination of the support vectors. And then when we calculate this prediction score, right? When we calculate dot product between the optimal weight vector and X, right? So it is essentially equivalent to calculating between the dot product between every training example and the test example X. Of course, weighted by alpha I stars, right? Does it make sense? Right? We just substitute the form of W star for W star, right? And because W star is represented as a linear combination of all the training examples weighted by alpha i's, right? And then you calculate this prediction score, you see that, okay, this prediction score is determined by the dot product between every training example xi and x. We only need to compute dot products between training examples that are support vectors and new example x. And now consider if we map our feature vector x into another space. This relates to our intuition about how to perform nonlinear classifier, right? Remember, if in the original space, we cannot find linear classifiers, an intuitive trick that, okay, if we come out some kind of nice, smart feature mapping, which we denote by phi, right, or phi, right? And then in the mapped feature space, we do some, we learn some linear classifier. we can imagine in the mapped feature space, the optimal V vector will still be a linear combination of the training inputs, but now the training inputs are represented by the mapped feature vectors from the original training input, right? And then apply it to the prediction. You're gonna need to compute the dot product between every training example and test example after performing the feature mapping. Right? Right. Here we call this example, right? In this example, in this plane, we actually cannot find any linear classifier, right? But if we can come out some nice feature transformation, right, or feature mapping, we map them into a 4-dimensional feature vector, and it is easy to say in a higher dimensional space, we can find a nice linear classifier or hyperplane to well separate out positive and negative examples, right? So now we can imagine in this mapped feature space, we run our SVM dual, get some like learn feature vector, and then during the prediction, we just need to first perform the feature mapping, then calculate dot product. Any questions so far? Okay, so now, because in a mapped feature space, right? Suppose we perform some kind of feature mapping, right? During the prediction, we would like to compute the dot product between every training example and the test example after feature mapping. Let us define a function, right? A function k over x and z, right? The return value or the value of this function actually is first performing feature mapping over x and z through phi, and then do the dot product. This is our definition. And then if we look at our prediction, right? If you want to predict the label for a new example x, right? The calculation essentially is to compute over every training example, alpha I, yi, and then this function over xn, x. Remember, the definition is just the first performing feature mapping, like high dimensional lifting map, right? And then do the dot product. And then add them together and plus the bias parameter b, we take the sum. The question is, what does this new formulation give us? If we just change the notation, right? This is if we just will as the notation change, like I replace this dot product between phi x and phi z by some function kxz, then there's nothing meaningful in practice, right? Because no matter what kind of notations you use, right, you can still compute the feature mapping first and then do the dot product. But if we can come out an alternative way of computing k, meaning that we can directly compute k, x, and z in the original space, not evolving explicit feature mapping phi, then it will bring a lot of computational benefit, right? So imagine like your feature mapping x and z, right? Both and xc, original in the 2-dimensional space. Now you have to map them into like 1 million dimensional space. If you explicitly compute the feature map, that means, okay, you're gonna compute 2 1 million dimensional feature vectors and then calculate dot product element-wise and wise, right? That will be very expensive. But if you can come out the computation technique, right? Namely computing the value of k without doing this. Maybe you just compute x plus z and times something else, right? I'll take the square root, I'll take the polynomial upon that, whatever. You just compute this k value in the original feature space of x and z without explicitly performing feature mapping, then it will make the computation a lot easier. right? If we can compute the value of k without explicitly writing the blown up representation, then we'll have a computational advantage, right? Such a computational advantage is called a kernel trick. So what does kernel trick mean? It basically means that I want to use a smart and much cheaper way to compute k, rather than explicitly performing a feature mapping over the input vector x and z, then do a dot product. So this is called kernel trick. And this is important because later we'll say in some feature mapping, example, some feature mapping, the phi here can be infinite dimensional. That means like you will never be able to explicitly write down or compute the feature, the map to feature vector, because it's infinite dimensional. Right? It's never been practical to do that. In that case, you have to leverage some kind of kernel trick to avoid explicitly computing the feature map. Okay, any questions so far? Okay, so now let us give some concrete example, right? To see why this kernel trick is valuable, right? So I'm gonna come out some kind of like simple feature mapping, which we call quadratic mapping, right? So suppose I have an n-dimensional feature vector. Right? My input vector is just n-dimensional, so I got n features, x1 through x1, right? And I want to extend or map this feature vector to a new dimensional space such that the new feature vector contains the polynomial of those features in order 0, 1, and 2. If you take a look, it will be 1 is actually polynomial of order 0, right? And x1 to xn, which are polynomial to the at order 1, right? Which actually include the original feature vector. But we also have the polynomial of order 2, right? You can imagine we got x1 square, x2 square, xn square, and also all the cross product between those features. All degree 0 terms, all degree 1 terms, and all degree 2 terms. So now I want to ask, right? If I want to compute the dot product after this feature mapping, what is the time complexity? Our input vector is n-dimensional, right? We first perform a quadratic feature mapping and then do the dot product. What's the time complexity? Any guess? Any thought? Just give me a guess. Yeah, it's n squared, right? Because remember, the number of the features, right, after quadratic feature mapping is at order of n squared, right? Because you have to combine all pairwise terms, right? So n squared, right? You have to do feature map for x and feature map for z. This has taken the complexity of n squared, right? And do dot product n1's product. Remember, the length is at n squared. So eventually you will get O(n) squared time complexity. And of course, the space complexity is also O(n) squared because you have to explicitly store this map to the feature vector, right? Does it make sense? Right? You can count, right? So you got all degree 0 polynomial
Just one, right? All degree 1 polynomial is n, right? And all degree 2 polynomials, how many terms do we have? Yes, n squared, right? But actually, you have to make it more like unique, right? You don't want to have duplicate terms. It's like a combination of n from 2 and plus n, right? Of course, it's about n squared, right? If you write it down as n over minus 2 and divided by 2 and plus n, right? So if you add them together, it will just give you O n squared. And imagine, suppose n is 1,000. Then what's the time complexity? It's 1 million, right? If n is 10 to 4, then it's 100 million, right? That's very, very expensive. But now I claim that the calculation of this dot product is equivalent to calculate in the original space following this way. Basically, we can first compute the dot product between the x and z in the original space. No need to perform any feature map. Then plus 1 and take square. The results are equivalent. But what's the time complexity here? What's the time complexity of this way of computation? Just O(n), right? Because x is n-dimensional, z is n-dimensional, dot product is O(n), right? Plus a constant operation like plus 1 takes square, right? So now you see the difference, right? So if n is 1,000, right, 10 to 3, the complexity 10 to 3, right? But if you just explicitly compute the feature map and dot product, it takes 1 million, right? And the larger the n, the more difference between the two complexities. This is huge. Okay, so let's stop here today. And on Thursday, we're gonna literally show why doing this two are equivalent.